Okay, awesome. So we'll get started now. So this is lecture two, and this is kind of continuing from where we left off last time. And we will actually kind of continue with the definitions of convex functions and kind of more of the basics of convexity. And part two of this lecture will actually we will start looking at gradient descent, and in particular we'll look at some proof techniques on gradient descent. So this is going to be slightly more involved mathematically. So you basically get an idea of some of the proof techniques that have been used. And again, as was pointed out earlier, I will actually post in the course webpage. Um, I will actually post on the course webpage the links to the sessions, or sorry, the kind of material that I'm using for each session, right? So that will help you for kind of further reading as well. So there's a question here: where can we access recorded lectures? So it should be available on YouTube. So I'm putting basically each recording on YouTube, but I'll actually share the link on Teams, and also it should be available also on Blackboard Collaborate, I believe, but you should be able to see it on YouTube. So I'll post the link to the lectures there. Yeah, thank you. Were there any other questions? Okay. So yeah, so as I said, the first part will be slightly more kind of sorry, this lecture will kind of be slightly more mathematical. So do stop me if you have any questions. I may not go over all the proofs today. I think what I'll do is I will probably post an optional lecture, which is like basically 2.3, right, where I'll actually go over some of the more detailed proofs, in more detail, and kind of spend more time on that. If you want, if you're interested, you can go over that. Okay. Awesome. So what we covered last time was basically the basics of convex sets and the definitions of convex functions. And in this lecture, we will actually look at, we'll kind of continue with the properties that we started off last time. So we'll actually look at properties of convex functions. Then we'll actually look at subgradients and essentially kind of subgradient calculus, right? So this is probably going to be useful for non-differentiable convex functions, right? And we'll also go over first order and second order convexity, and finally local and global minima, right? So I think this is still going to be setting the stage for kind of the first few lectures where we'll cover convexity. Once we kind of understand these concepts, I think we'll be in a position to basically understand some of the proofs involved in convex optimization. Again, I'm emphasizing that this course is more geared towards machine learning, right? So you may not see some of the standard stuff that you see in a typical optimization course, where you typically start with things like, kind of linear algebra and linear programs, and kind of build off to quadratic programs, semi-definite programs, and things like that, and finally convexity. And you study things like, interior point methods, etc. We won't be focusing as much on kind of those topics in this course, right? Because this is kind of more geared towards machine learning. Okay, so again, a recap of some of the properties that we discussed last time, right? So I'm just kind of recapping here, and then we kind of move on. So the first property is non-negative weighted sums. So essentially, as long as the alpha i's are greater than or equal to 0, the sum of I from 1 to n alpha I fi of x is convex. If fi of x are convex for all I, right? So this is kind of straightforward. The next property is compositions with affine functions. So this is actually really important to go from one dimension to kind of n dimension, right? So many machine learning loss functions, or in general, many kind of convex functions that come up in practice, which are kind of n-dimensional functions, turn out to be of this form, right? So basically, f here is a scalar convex function, right? So f is a function that goes from R to R, right? And ax plus b, so x itself belongs to R raised to d, right? So if it's a d-dimensional function, but the transformation ax plus b basically gives a scalar quantity, right? So this could give a scalar quantity, or it could be a vector. It depends from function to function. But imagine that a itself is a vector in R raised to d. Then this is essentially a kind of convex function as well. But this could also be a matrix, in which case the matrix case is where f is a function from R raised to m to R, and in this case a here is a matrix which is R raised to m cross d, right? So basically both variants of these functions are convex. But this is typically useful, for example, in machine learning, where you have a scalar case, right? So basically this particular case, so you have a scalar function and then you compose this with a affine kind of vector value. Okay. So an example of this is this kind of log barrier, right? So you have bi minus ai transpose x for all I is essentially a kind of affine function, right? And minus log of x is convex, so that's why this log barrier is actually a convex function. Actually, another function which I have not added here, but which you know all of you are very familiar with in machine learning, right? Is essentially log of 1 plus exp raised to minus w transpose xi, something like this, right? Or maybe there's a y here. So exp raised to minus yi multiplied by w transpose xi plus p, right? So this function is, can someone tell me what this function is? Logistic loss, right? Exactly. So this is the kind of logistic regression kind of function. Again, this is in a very similar form, because you can define an affine function, right? So an affine function a of x or ai of x is equal to minus yi times w transpose xi plus b, right? And then you can define f of, or actually here this is in terms of x, right? So you can define f of x now to be log of 1 plus exp raised to uh, ai of x, right? And we saw this last time that this function is actually convex, right? So log of 1 plus exp raised to something. This function also is also called log sum x, right? So this is actually more general a convex function, right? So if you have a sum of exponentiated terms, right, and you take the log, and each of these are affine functions, for example, then this function is actually convex, right? But yeah. So essentially, sorry, I'll just write down over here that if you define g of z to be, um, or maybe let's do the following. So sorry about that. So let's define f of z to be log of 1 plus exp raised to z, right? So then finally, our function in logistic regression is actually equal to, I'll call this g of x. So g of x is actually equal to f of ai of x. Any questions until now? Right. So this is just a review from last time. Um, this is kind of a nice property that would be used to kind of transfer the intuition that we know from scalar functions to kind of vector valued functions. Right. It turns out that another example of this is a norm. So you take ax, kind of ax plus b, and you take the norm of this, right? This also is a convex function, right? So a norm of an affine function is convex. Again, so if you recall, the norm itself is a convex function, right? So we saw this last time that um, f of z equal to the norm of z for any norm is convex. All right. So we also saw this last time. So we kind of ended at this point. So compositions with scalar functions can also lead to convexity under certain scenarios, right? So if you have a function h which is convex and non-decreasing, right, and g is convex, right, or g is concave and h is convex and non-increasing, right? So if you have these two scenarios, these two specific scenarios, then in general, you can show that F will also be convex. So it could be the case that under certain special cases, right, you do not require H to be, for example, convex and non-decreasing, and this will still be convex, right? But this is not true in general. Okay. So one such special case is in fact the affine function case, right? Because the affine function case, you have gx to be kind of ax plus b, which is this affine function, right? And here we do not require any kind of extra property on H. We just require the convexity of H, and this will kind of ensure um, the convexity of F, right? But in case for kind of more specific cases, we require the H itself to be either convex and non-decreasing or concave or convex and non-increasing if G is concave. Okay. A simple way to show this is actually take a double derivative. So in fact, it's easier to just prove this in m equal to one, the m equal to one case, so the one-dimensional case, where G itself is actually, so this should be n equal to one. Sorry about that. So where G itself is the one-dimensional function, right? And you can actually kind of expand upon the fact that G is either convex and H is convex and non-decreasing, or G is concave and H is convex and non-decreasing, and basically use these two to actually use a chain rule to kind of find out the double derivative of f prime of x. So the proof actually is fairly simple. I would encourage you to maybe offline try to derive this yourself, and see if you can show this. The general case is slightly harder because you need to do kind of matrix algebra there, and you need to use the kind of matrix version of the chain rule. So it's a little bit more involved, but it's still possible. The idea still remains the same. Okay. Um, One thing to note that in the vector valued function, this is a matrix, right? So here del square f would be greater than equal to 0 in a positive semi-definite sense, right? So this was actually brought up last time. Thank you. Okay. So examples of this is fx equal to exp raised to fx, or maybe I should say fx equal to exp raised to gx is convex if g is convex, right? And similarly, 1 over gx is convex if g is concave, right? So these are kind of again two examples of this particular paradigm. Okay. The same extension of this holds in the vector compositions as well, where now h is so basically g is this function that goes from r raised to n to r raised to k. So essentially, the output of g itself is a vector, right? So essentially, you can write g of x to be nothing but g1 of x to be up until gk of x, right? Where each of these gi's of x are itself kind of scalar convex functions. So then you can define this H to be a composition in this way, right? And in fact, this is kind of repeatedly used in machine learning, by the way. So we have compositions, particularly in deep learning. And here to kind of ensure convexity, we require that the GIs to be convex and H to be again convex and non-decreasing in each argument, and the GIs to be concave and the H to be convex and non-decreasing again in each argument, right? So again, the examples are kind of simple versions of this. That if you have a sum of I log of gx, this is concave if g is concave and positive, and you have actually this log sum x, right? So you have the log of the sum of exponents of convex functions, and this function is convex if the GIs are convex, right? So kind of both of this is can be proved using this particular nice property of convex function. There was one interesting question brought up last time. Um, I don't remember who it was. Was it Abhijit or I don't remember. But this was an interesting question that in deep learning, right? Yeah, so it was Abhijit. Yeah, thank you. So in deep learning, we have compositions of various functions, right? So maybe I'll just kind of have a slide aside over here, right? So in general, in deep learning, we have essentially kind of functions like this, where you essentially have psi1 of um, sum of I from 1 to say m1 of wi psi 2 of and so on, right? And each of these are basically kind of non-linearity, or I'll just call them non-linear functions, right? So examples of non-linear functions are, for example, the sigmoid, or tan h, or actually something that is kind of being used a lot, which is rectified linear, right? And rectified linear is nothing but you take a max of something like x comma 0, right? So it's kind of a function, something like this. So the function brought up last time is that this could be convex, potentially, right? So basically, since you have these kind of arbitrary compositions, it would not be convex in general, right? But there is a scenario because this max of x comma 0 is convex, that potentially this could be convex, right? So one issue in deep learning is that we do not actually constrain the weights, the wi's, right? So essentially, these weights could either be positive or negative. So in case we actually constrain the weights to be, say, positive, then it is possible that we can actually construct kind of convex compositions of functions. And I think there have been a few papers that have been kind of studying this, right? So this is kind of an interesting point. But again, since most of deep learning is not really focused as much on, just because it's convex, it somehow, is good. Kind of more and more, what people have been finding, that it's more important to actually model the to have the model as rich as possible. And it turns out that just doing very simple tricks like stochastic gradient descent, which we'll actually cover in this class, and variants of stochastic gradient descent, actually turn out to perform pretty well even theoretically, right? So more and more people have been studying kind of theoretical properties of non-convex optimization and trying to show properties, probably even in certain cases global convergence, right? So this is kind of one caveat I wanted to mention, that it's kind of possible to come up with convex compositions here for deep learning. Okay, all right. So I think at this point we'll actually start with this lecture. So one of the first properties is that pointwise maximums and supremums are also convex, right? So if you have convex functions f1, f2 until fm, why should we constrain the weights to be greater than or equal to 0? Um, so you need to constrain the weights to be greater than or equal to 0 because you are doing, yeah, so you kind of want this to be non-negative, right? And since you're doing compositions, you would eventually have compositions of functions which are kind of, you have non-negative compositions, and then you don't necessarily have the non-decreasing kind of property, right? Okay, so if you have f1, f2 until fm as convex functions, then the max of f1x, f2x until fmx is also a convex function, right? So in particular, you can show that if f of x is the sum of the r largest components of x, right? So this is the notation here, which is x1, x sub 1, x sub 2 until x sub r. right? And x sub I is the ith largest component of x, then this function is a convex function, right? How can you show this? Any thoughts? How can we use this fact that we have a max of a finite number of functions to actually show that the sum of the r largest components of x is convex? Anyone? Any ideas? So think of the following, right? So think of this where you have the function fi of x, right? Or actually, okay. So maybe instead of writing this down, I'll kind of give the intuition first, right? So you kind of want to take the sum of the r largest components, right? So essentially take all possible subsets of size k, right? So x here is a subset of say n, right? And given any subset of x, you basically can define this function as the sum of x j in x um, xj, right? So xj is the jth component over here. So now what you can think of this is this function f of x is actually nothing but taking a max over all possible subsets x such that size of x is equal to k, right? So essentially I take all possible subset sums of k quantities, right? And I take the max amongst them. This is a simple kind of linear maximization. This maximization will be nothing but the sum of the r or sorry the r. So actually in this case this is r. Right? Sorry about that. So to take the sum of the r largest components of x, right? And since this is going to be finite because in some sense there are only kind of n choose r number of possible subsets of size r, right? So essentially, we just need to basically look at these finite number of subsets and take the max of this, right? So basically, m over here is in choose r. Any questions on this? Okay. So the same actually extends to pointwise supremums as well, right? Okay. Um, so essentially so maybe instead of going into the math, I'll just give the main intuition, right? So the intuition is you are taking the sum of the r largest components of x, right? So you take all possible subsets of size r and you try to maximize the subset sum over all these subsets, right? Over x. And the max value of this will be nothing but taking the sum of the r largest components, right? So in some sense, what I'm doing is that I'm rewriting f of x, which is equal to x1 until xr, right, as f of x equal to max of this, right? So in some sense, I'm kind of transforming this function of the sum of the r largest components into a pointwise maximum over a kind of set of functions, right? And each of these functions are nothing but linear functions of this form. Does this help? Okay, awesome. Thank you. So next we'll actually kind of extend this to pointwise supremums as well instead of maximum. So this is kind of a technical point, but you can kind of extend this now to even this being a continuous set of quantities, right? And you can kind of look at the supremum instead of the maximum. So essentially an example of this is take g of x to be the sup of y in s f of x comma y, right? And this function is convex if f of x comma y is convex. So and kind of an example of this is the maximum eigenvalue of a symmetric matrix can be written as lambda max of x equal to sup of y in s x, basically this particular quantity, right? Okay, so I think this is probably all on the properties of convex functions. So can you quickly tell me which of these functions are convex? So is the first one convex? Is L1 or L2 regularized logistic regression convex? Yes, it is, right? Similarly, SVMs, is it convex? SVMs also are convex. Similarly, multi-class logistic regression is convex. Least squares is convex, right? Sorry. So essentially, the main intuition here is to again try to come back to the scalar valued functions and try to kind of have an intuition whether these same functions turn out to be convex in the kind of multi-valued scenario, right? And kind of all of these are um, machine learning loss functions, right? Okay, so now we'll actually kind of talk a little bit. Yes, Sanjay.
Professor, so are there machine learning functions that are used like before deep learning that are actually non-convex but they still work in practice?
Yes, yes. So example of this is PCA actually. So PCA involves a non-convex optimization, but still, interestingly, PCAs have been shown to kind of um, give actually work out. So in fact, you can show that you can get the global minima in the case of PCA by kind of reformulating the problem slightly. Another example of a non-convex function is actually this is kind of this softmax contextual bandits. So this function turns out to be non-convex, and the again this is something that still kind of works out in practice, even though it's non-convex. This one, though, theoretically, it's much harder to show that you know you can kind of get something that is close to optimal or something like that. But this is non-convex. Yeah. But kind of having said that, it's relatively rarer to have non-convex functions because a lot of machine learning was kind of the intuitions of loss functions tended to be convexity, right? So one of the conditions in the pre-deep learning era that people were looking for was convexity of loss functions because you can then provably show guarantees and so on and so forth, right? Only after deep learning came was there kind of a realization that even if it's non-convex, it's still
I
okay,
see.
right?
Okay.
Yeah. Any other questions? Okay. So we'll also look at this concept of a direction vector and a bit and basically kind of directional gradient, right? So you kind of take any direction here as x in r raised to n, and you can represent this kind of kth component by xk, and uk here is a unit vector pointing in the kth coordinate, right? So essentially uk is a unit vector over here. Um, and essentially, kind of building upon this now, we can come up with the notion of the directional derivative, right? So the directional derivative of f of x at x. So this is the derivative at a particular point x, right? And in the direction of a unit vector v is given as this quantity, right? So essentially, the intuition is you. So this is again we are kind of dealing with vector valued functions here, right? So we have or sorry, we're kind of dealing with functions that are defined on vectors, right? So these are functions defined on kind of d-dimensional quantities. So the gradient is essentially going to be a vector, right? So now the question we can ask is that suppose I want to define a derivative in a particular direction, right? So this concept is given by a directional derivative. And the directional derivative dv of f of x, right, in the direction v, is given as the limit of h going to 0. So this kind of gets back to the standard calculus, right? But this is very intuitive. So the intuition here is that I take a step of size h, right, a step of size h in the direction v, right? So I add x plus hv. So I'm looking at a particular direction and I'm subtracting x divided by h, right? So essentially, I'm given a point here in n-dimensional space. I have a vector direction v, right? So what I'm doing is that I'm adding kind of a hv to x in this direction. I'm constraining only in this direction, right? And I'm taking the derivative over here. So in some sense, you can kind of treat this as, um, or sorry, you can kind of define this as g of h now as f of x plus hv minus f of x, right? So now I'm basically taking the limit of h going to 0 of g of h divided by h. So it's easy to see that in fact the directional derivative, if you take the unit directions, right, uk, which are the unit vectors, um, is nothing but the gradient in the kth dimension, right? Why is this? Because this is how the gradient is defined, right? You're taking a partial derivative for each of the xi's. So essentially, what you're doing is that your v over here is a unit vector. So only in the direction k is it non-zero, right? Everywhere else it is zero, right? And then you are basically taking the x plus h in this kth dimension minus f of x, right? So keeping everything else constant, you're just kind of changing the kth dimension here, which is nothing but the definition of the gradient, right? So it turns out that using the gradient, we can kind of give this nice compact form of the directional derivative. So the directional derivative dv of f of x is nothing but the sum of k from 1 to n of the gradient of f(x) multiplied by vk, right, in kind of each axis. So basically what this means is that this is nothing but the dot product of the gradient vector dot with the v vector, right? So in some sense, this is kind of the main relationship of directional derivative that we'll be using. And this becomes useful particularly in optimization problems, because sometimes we want to take a descent direction, not necessarily in the gradient direction, right, but in a slightly different direction. So we can use this notion of directional derivatives over there. Okay. All right. So now we can kind of link back convex functions with convex sets, right? In fact, this is something we kind of alluded to even last time where we spoke about norms. So we can define a sub-level set, okay? And in particular, we'll define an alpha sub-level set. So the alpha sub-level set of f is nothing but a set of points x in D, right? D is the domain of f, such that f of x is less than or equal to alpha, right? And this is actually interesting because if you recall, we spoke about kind of this in the context of norm balls, right? So we have a norm ball as nothing but, I'll call this norm ball n alpha, right? As nothing but the set x of x in D such that the norm of x is less than or equal to alpha, right? And this function can be defined with any norm, right? And with any norm, this is a convex set. So in fact, the norm ball result that we showed last time is nothing but actually a special case of this alpha sublevel set. Right? In fact, this doesn't necessarily hold for um, just the norms, right? But this holds for any arbitrary convex function. The alpha sublevel set can be defined in this way. And in fact, this result basically is the main result here, right? It shows that for any convex function, if f is convex, the alpha sublevel sets will be a convex set, right? And again, kind of circling back with the norms here, we see that since the norm is a convex function, this shows that the norm ball also is a convex set. Okay, so I'm actually not going to prove this right now, but the proof is actually very similar. Yeah, this actually holds in one direction only. Yeah, thank you, Professor Chandrasekhar. So this actually holds in one direction only, and we'll actually talk about why this is not if and only if. So um, the proof of this is very similar to the proof of the norm ball, right, that we showed. Basic idea is that we just use the convexity of f, right? So if f is a convex function, and you have this basically, okay. Essentially, you consider x1 and x2 to be in L alpha, right? And since they belong to L alpha, you have f of x1 less than equal to alpha, f of x2 less than equal to alpha. Then what we do is we basically use the convexity, right? So we have theta x1 plus 1 minus theta x2 also belongs to D. And then we use the convexity of f over here, right? So you take the convexity of f and then you kind of plug in alpha and then you get this. And essentially what this means is that if you just look at this and this will show that f of x is less than equal to theta alpha plus 1 minus theta alpha, which is nothing but alpha, right? So this means that f of x also is less than equal to alpha, where x is this convex combination of x1 and x2, right? So this implies that x also belongs to the L alpha f, which shows that L alpha f is a convex set. So this is the point, right? That though L alpha f is a convex set, the converse of this result is not true. So in particular, what it means is that just because a sub-level set of a particular function is convex doesn't mean that the corresponding function is also convex, right? So the sub-level set of a function could be a convex set, but that function may not be a convex function. So an example of this is actually f of x. Sorry about this. So f of x equal to x2 divided by 1 over 2 x1 square. So it turns out that this function is not convex, and this can be shown by just taking the Hessian and so on and so forth, right? This is a two-dimensional function, and you can kind of show this. You can actually show that the zero sublevel set actually is convex, because the zero sublevel set is nothing but x2 less than equal to 0, right? So this is an example where one particular sublevel set is convex, but the function is itself not necessarily convex. In fact, such functions are actually called quasi-convex. So functions where all its sublevel sets are convex are actually called quasi-convex, right? This is another example. I'll kind of go over it very quickly. This is kind of the standard normal distribution function. So you take f of x to be 1 minus minus 1 over sigma square root 2 pi exp raised to minus x minus mu square over 2 sigma square, right? So it's easy to see that you can essentially define. So basically, with this, you can actually show that this function actually is not convex, right? But this is quasi-convex because you can actually show that for every sub-level set, you have essentially this particular expression, right? And this turns out to be nothing but essentially ellipsoids, right? So the sub-level sets of this Gaussian function turns out to be ellipsoids, right? Which shows that Gaussian functions are quasi-convex. Right? So quasi-convex are this kind of richer class of convex functions. So if you have the class of convex functions, right? So this is convex. Quasi-convex functions are bigger, right? Why are they bigger? Can someone tell me why they are bigger? Or maybe in other words, can someone tell me why a convex function is also quasi-convex? Yes, Nathan.
My intuition is that if you have a convex function and you took any sublevel set for it, that would also be convex. So if you have a convex function, you can show that it's also quasi-convex, meaning it's a subset.
Exactly, right? So a function is, so this is a definition of quasi-convex function. So a function is called quasi-convex if all its sublevel sets are convex sets, right? And by basically, as we proved in the last slide, for a convex function, all its sublevel sets are convex sets, right? So this means that a convex function is also quasi-convex, right? But the converse doesn't hold. So that means that quasi-convex functions are not convex. And an example of this is this kind of normal distribution function, right? So which means that quasi-convex functions are a much larger class or a strictly larger class compared to convex functions. Yes, Nathan.
I just wanted to make sure I'm not confused by the slides. On slide 13, it says that every quasi-convex function is not convex. Should it be not every? or sorry, not every quasi-convex function is convex, but some are.
Yes.
Okay.
Yes. 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 Okay. Okay. I'll actually correct the slides. So actually, I can't somehow see it. Where are you pointing to? Is it this slide, slide 13 or slide 12?
Yeah, slide 13. I was just confused by the wording at the very end of.
Oh, I see. I see. I see. Yeah. 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 So not every. Yeah, that's right. That's right. So I'll actually correct this one. Thank you. Okay. Um, another related property is actually epigraphs, and here we actually have a if and only if condition. Again, I won't actually prove this, but the proof is there in the slides, so you can kind of go over this offline. In the interest of time, I won't actually kind of prove this right now. But you can define the epigraph of f as the set of x comma alpha, right? So if x is a r raised to n function, right? So that means that b is a subset of r raised to n. So this means that x belongs to r raised to n, right? The epigraph is a set that actually lies in r raised to n plus 1. The reason is because it is x and it is a scalar quantity alpha, right? So it's basically pairs of x and alpha, or this basically n plus 1 dimension of x comma alpha, such that f of x less than equal to alpha, right? For x is x in D and alpha in R, right? So all x and alpha that satisfy this property is the epigraph, right? So in some sense, the epigraph is a set of points that lie above the graph of x, right? So imagine that you have a convex function, right? So say you have this kind of bowl-shaped function, right? Then essentially what you're doing now is you're taking this set. So this function is a one-dimensional function, right? Because this is f of x and this is x, right? But now my epigraph is a two-dimensional set, right? And I'm taking this entire kind of region over here, right? And this region is a convex set. So, okay, so the theorem basically says that let D be a non-empty convex set, that is a domain, and f is a convex function. Then f is convex if and only if the epigraph of f is a convex set. Okay, so here the proof basically goes in two steps. So to prove an if and only if condition, right? Again, this is just a takeaway for when you're proving things. So if you're claiming something is if and only if, you want to first prove that. So suppose basically one quantity is identical to the other quantity. You want to prove that the first quantity implies the second quantity, and the second quantity implies the first quantity back, right? So we'll start by proving that if f is convex, this implies that the epigraph of f is convex. Okay, and this is the proof. The intuition of the proof actually is similar to what we saw in the convex sets. Again, you know that f is convex, so you can basically take a theta such that theta x1 plus 1 minus theta x2. You also have this convexity kind of relationship over here, and then you basically know that your theta is between 0 and 1, so theta plus 1 minus theta sums up to be 1, right? And kind of following through this, you can actually show now that this particular point, which is theta x1 plus 1 minus theta x2, comma theta alpha 1 plus 1 minus theta alpha 2 also belongs to the epigraph of f, right? So this proves the first direction. And to show the second direction, we start with the epigraph of f being a convex set. And if the epigraph of f is a convex set, then we know that essentially theta x1 plus 1 minus theta x2, comma theta alpha 1 plus 1 minus theta alpha 2 belongs to the epigraph of f, right? Which implies that this must hold, right, for any theta. And actually, this in fact proves convexity, right? So the other case is in fact even easier to show. Okay, so any questions until now? So far what we have done is we have basically looked at some properties of convex functions, and then we kind of looked at this connection between convex functions and convex sets, right? Yes, Professor.
So it is this epigraph that distinguishes convex functions from quasi-convex functions. Quasi-convex functions epigraphs are not necessarily convex sets.
Yes, 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 yes. This is a great point actually. So thank you. So actually, I'll add this over here. So essentially, so again, this is because of this if and only if condition, right? So for quasi-convex functions, so if f is quasi-convex, the epigraph of f is not necessarily a convex set. In fact, it will not be a convex set because of the if and only if condition, right? So this like exactly. So this is what distinguishes this kind of this is what distinguishes quasi-convexity from convexity. So thank you. This is a great connection. Okay, so with this now we can actually we'll kind of shift gears a little bit and look at first order convexity conditions. So again, this is going to be important for us when we are going to be looking at algorithms in lecture 2.2, right? So essentially, the first order convexity conditions state that for a differentiable function f, right, and a convex set D, f is convex if and only if, right? Sorry. So again, actually, I have not added the proof of this again in the interest of time, but I will post a slightly longer version of this slides on GitHub, right? And which will actually give a proof of this particular result as well. So it's actually kind of a proof in 4 to 5 slides, which is actually possible to show for each and every one of these if and only if results, right? Okay, so a function f is convex if and only if the following result holds, right? That for any x and y, we have f of y greater than equal to f of x plus the gradient of f of x transpose y minus x, right? So this is basically the result that shows that that in some sense this is a linear lower bound of f, right? So essentially, if we fix x, right, then you can essentially look at f of y, which is greater than equal to essentially this linear function hx of y, right? So hx of y now is a linear function that is f of x plus gradient of fx transpose y minus x. So basically what I've done here is I've fixed a x. So for fixed x, I vary y over y, this gives a linear lower bound, right? So this is nothing but the kind of known result that we know that if this is a convex function, you take a point over here, right? And this is a linear lower bound everywhere, right? So I have my fixed x, right? So for all y, for every other y, f of y is above this, right? So this result holds as an if and only if condition. Okay. Similarly, you can show that if f is strictly convex, so basically f is strictly convex if and only if this inequality holds with strict inequality, right? So it's a strict inequality, so it can't be equality anywhere. And finally, you can also show a strong convexity result, right? So f is strongly convex if and only if for some constant c greater than 0, f of y is greater than f of x plus this quantity, right? Plus an additional term, which is half c multiplied by y minus x square, right? So this basically shows that for a strongly convex function, you have a quadratic lower bound everywhere, right? So for any convex function, okay, so the intuition is that for any convex function, right, you have a linear lower bound everywhere, right? Now note that in the case of linear functions, if a function is linear, then this kind of matches, right? So for a linear function, the lower bound is equal to the function itself, right? So that's why we have the strictly convex function. So a strictly convex function is a case where apart from x, everywhere else it holds with strict inequality, right? So by the way, this is like for x not equal to y, right? So for every other point y not equal to x, it holds with strict inequality. Okay, and a strongly convex function. So a strongly convex function essentially has a quadratic lower bound, right? So sorry, maybe my drawing is not accurate, but imagine that this is a quadratic function, right? So that means that I have my f of y, and f of y is actually greater than or equal to this quadratic function of y, and this quadratic function is nothing but this. So there is this additional term. So the quadratic function. So Nathan, I'll just give you just give me 1 minute. The quadratic function is this linear function plus half c times y minus x squared. So this c is also called the strong convexity parameter. Yes, Nathan.
So I had two questions. One is, why are we adding 1/2 c to the function? And two, is the condition is it such that there exists a c greater than 0 such that for any x and y, or is it for any x and y there exists some c?
No. So essentially so essentially there is a fixed c, right? Such that for any x and y, this inequality holds, right? And this c is called a strong convexity parameter. And to answer your question, why there is this half? So if you recall the definition of strong convexity, right? So the definition of strong convexity, if I recall, right, was nothing but the fact that we require f of x minus mu by 2 of x square to be convex, right? So this mu is nothing but the same as a c. So essentially c is nothing but mu. So c is the strong convexity parameter, which is mu, right? And this basically is the reason why you have this half over here. So essentially this is just kind of a convention that people have been following for strong convexity, that you have a half, and this kind of makes a lot of the analysis easier. You can remove the half and then you just have a 2 over there, and so on and so forth.
Right, but my question is not necessarily why the half is there, but why in this case we're adding it, but in the definition we're subtracting 1/2 c.
Mm-hmm. No, it's yeah. So it just turns out so the intuition is the same, right? So all we are saying over here is that when we subtract this mu by 2 x square, we are still kind of convex, right? So this means that it is somehow larger than this when you look at the first order condition. Yes, Professor.
The 1/2 is normally there for quadratic things, so that when you take derivatives, the half and the 2 cancel out. That is the only reason.
Yeah. Yes. That's a great point. Yes, exactly. Yeah, that's right. So basically in all the analysis you'll be taking derivatives, right? And that's where you get this half condition, right? So coming back to Nathan's question, the intuition here, right, is that the function is still convex. Okay. So the way you can prove this is apply the first order convexity condition on f of x minus mu by 2 x square. Okay. And so essentially all you're doing is that you're just applying this relationship, right, this result on this term, right? So the intuition here is that in some sense, even after subtracting this mu by 2 x square, right, we are still convex, right? So what that means is that my function f of y is greater than this linear function plus this quadratic term, right? Because this quadratic term in some sense offsets this mu by 2 basically x square. So that's the intuition. But in some sense, you can kind of see this result only when you substitute back the strong convexity assumption, right? And substitute over here, and you will get this result, right? So the intuition again is that the function has to be growing larger than a quadratic function. So it has to be a quadratic function plus something else. Okay. Are there any other questions? Okay, great. So we will also look at the second order conditions of convexity, and this is what we kind of alluded to earlier as well. So the second order condition of convexity basically says that the Hessian matrix is positive semi-definite, right? And this is the symbol of positive semi-definiteness. Um, so it's essentially you kind of compute the Hessian and then you basically check for the positive semi-definiteness, right? So in one dimension, this means that f is convex if and only if the double derivative is greater than or equal to 0. And by the way, this result also is if and only if, right? So f is convex if and only if the Hessian matrix is positive semi-definite, right? And the same holds for the one-dimensional case as well. Okay, so another kind of interesting kind of relationship over here is that um, is kind of the so-called monotonicity of the gradients, right? So what I mean by monotonicity of the gradients is again, this is kind of analogous to the one-dimensional case, right? So if you recall, we had this result in the one-dimensional case where given a convex function, right, and you take x1 and x2, right, then if x1 is less than equal to x2, right, we have that the gradient of f, again, this is a one-dimensional function. This is just one-dimensional, right? So the gradient of f, which is a scalar quantity, will also be less than equal to the gradient of f in x2, right? So in some sense, in one-dimensional space, the gradients were monotone, right? Now, the same monotonicity is not very clear in d dimensions, right? So in higher dimensions, what do you mean by monotonicity? So one way to kind of capture monotonicity is by taking the difference between x minus y, right? And a dot product between x minus y and the difference in the gradients, right? And the dot product between the two is greater than or equal to 0, right? So what this means is that if x minus y is in one direction, right, then we want the gradients also to be roughly in a similar direction, right? It may not obviously be exactly in the same direction, but you want it to be roughly in the similar direction, right? So we don't want that if you know x minus, if a vector x minus y is in one direction, then the gradient vector is in kind of an opposite direction, right? So that would be then, so then in that case the dot product would actually be less than 0. So we want them to be roughly in the same direction, right? So this is not the case. Okay, so this is the result stating this property, and in fact this property holds very easily from the first order convexity, right? So all you need to do is just kind of note that f of x is greater than or equal to f of y plus this, and f of y is greater than or equal to basically gradient f x transpose y minus x, and you just add the two, right? So you just add these two results, and lo and behold, you'll exactly get this simple relationship, right? So adding both inequalities above, we get the result. Also, like as I mentioned, the one-dimensional monotonicity statement we saw earlier is actually a special case. Okay, so now for the rest of this particular part one, we will look into some of these kind of subgradient properties of convexity, right? So essentially for a convex function, we saw that this result holds. This is the first order convexity. Right. So the first order convexity, again, there was a question about the intuition. Sorry, I think I missed this question. But the intuition basically is exactly this, right? And also as Professor mentioned. So you have kind of a linear lower bound for f everywhere, right? And for a convex function, we need to have this linear lower bound everywhere. So imagine you have a function like this, right? Then you take a linear lower bound over here, or you take the subgradient. So essentially, this is kind of related to the subgradient, as we will see, right? Then this is not a linear lower bound everywhere, right? So that's the reason why this function is not convex. So you take any point, you draw this linear lower bound. This linear lower bound will be nothing but this quantity, which is f of x plus gradient of f of x transpose y minus x. You take this quantity everywhere, right? And this will be kind of lower than the function. So if this is true, then this function is convex. So an obvious question is that how do we characterize these functions if the function is not even differentiable, right? So this is an example of a function where at this point here you have a non-differentiability, right? So this is not differentiable at this point. Why is it not differentiable? Can someone tell me why is it not differentiable? Again, this is 101 of calculus. Um, any thoughts? Okay. Actually, I don't know what crease means.
I mean, like if you looked at it from the limit perspective, if you approach that
Yeah.
point from the left, you got one value. If you approach it from the right, you got another.
Yeah, exactly. I think the others also answer. So essentially, you kind of have this point which is something like this, right? So this is kind of a smooth curve, and say all of a sudden this becomes like a straight line, right? Then now you go slightly in this direction, and the slope of this will actually be different than the slope that you go in the right hand side, right? I don't know if this is clear, but essentially what I'm saying is that you kind of take a limit, you take a R limit, right? Sorry, kind of take a R limit and you take a L limit, right? And the two of them are not going to be equal. Okay, um, so the question then is that how do we characterize again subgradients? And this is something that you have seen in machine learning. So I'll go over this quickly. You can characterize subgradients as now a set of lines, right, which give linear lower bounds everywhere, right? So essentially, what this means is that now given this curve, we have essentially this set of lines that give linear lower bounds, and similarly you have this set of lines here, right? So what this means is that now you can take any line in between the two, right, and this would also give a linear lower bound. Okay, so essentially what this means is that this region here corresponds to the set of all possible subgradients. Note that you cannot take a point which is say over here, right? So if you take a line here, this will not be a subgradient, even though it's a subgradient in one of the cases, right? It's not going to be a subgradient um, uh, basically everywhere, right? And similarly, you take a line like this is not going to be a subgradient, right? So set of all lines is convex. Yeah, exactly. So this basically gives now a set of points, right? And this set of points is actually called the subdifferential, basically at any given point, right? And there are some very interesting properties of the subdifferential, like as Professor was mentioning over here. And again, we won't be kind of covering a lot of this in detail, but I think just kind of the high level intuition of what subgradients are. So we look at a few example functions and we'll see how to compute subgradients, right, and subdifferential. So subdifferential again is a closed convex set of all subgradients, right, of a function f. So this is basically the subdifferential of f. So this is a notation that is typically used, the subdifferential of f. And in fact, I will talk a little bit about discrete analogs of this in submodularity. Like we'll be talking about the discrete subgradients and kind of supergradients and subdifferentials in the case of submodularity as well. So just kind of recall all of these concepts when we study this, right? So the pointwise maximum of a set of points. So if you have f of x, then you define basically max of I from 1 to m of fi of x, right? So you consider this function. So this function we saw is convex, okay? But very likely this function actually is not going to be differentiable, right? Can someone tell me why it will not be differentiable? Any thoughts? The max is not differentiable, right? So so think of it from this perspective, that you have two functions. Again, in fact, this function over here, right, itself can be seen actually as a max of two functions, because you have kind of this function over here, right, maybe goes something like this, and you have another function here, right, which goes like this. And you're taking now the pointwise max of both these functions, and you have kind of come up with this, right? So what happens is at the point where these two functions meet, the slopes may not align, right? So that's the reason why this function is not differentiable. It could be possible, by the way, that the slopes are exactly identical magically, right? And in that case it could be differentiable. But in general, the slopes may not align when you take this max. So that's the reason why in general this max function may not be differentiable. So the subdifferential in this case actually has a nice property. So it's a convex hull of the subdifferentials basically at the set of points where these functions meet, right? So in some sense, what this means is that, again, coming back to this example, right? So over here, these functions meet at this point, right? So at this point, we want to take a look at the possible subgradients of this, right? And we want to take the possible subgradients of this, and we take a convex hull of this, right? So convex hull of this will give nothing but set of points. So this result actually is kind of very powerful and can be used to show um, the subdifferentials of many functions. Okay. By the way, the same actually holds for kind of more general pointwise maximums and kind of supremums, even where this set here is like non-finite, for example, right? You can still define this kind of convex functions and the same intuition here. So in fact, like a lot of these functions are called polyhedral functions, and a lot of this is covered in kind of more advanced optimization courses. In fact, I think Professor Chandrasekharan's course also, he might cover some of the polyhedral functions and kind of connections of this with discrete optimization. In fact, a lot of this is there in Shriver's book. But for now, we'll actually look at a kind of more simpler functions. So we look at this function which is max of W transpose X comma 0, right? And again, this is a very simple function. In one side, it is a linear function, right? So imagine your W transpose X is like this line, right? So it is a linear function in one case, and in the other case, it is 0, right? So this point is the point of non-differentiability, right? So the question is that, so in fact, the non-differentiability holds at this region W transpose X equal to 0. Note that in this case, actually, the W transpose X passes through the origin, right? So this is a simple one-dimensional case, but in general, this is slightly more complicated. So so on this hyperplane, that is X such that W transpose X is equal to 0, we find the subdifferentials, right? So again, we look at the subdifferential. We basically look at the subderivative or the derivative or the gradient of W transpose X, right? So this is gradient F1, right? And this is gradient F2, right? So now I take a convex hull of the two subgradients, right? And essentially I get this convex hull of W comma 0, right? So this is nothing but that the sub differential is nothing but lambda times W for all lambda greater than equal to 0. Another illustrative example is lasso. Again, I'm kind of circling back in machine learning. So this is kind of going to be useful in machine learning as well. We have seen some of this in a machine learning course, but not in too much detail, right? So L1 regularization is basically for linear regression is half of y minus x square plus lambda times the one norm of x, right? Or the L1 norm of x. So the subgradient of x is the derivative of this, which is x minus y, right? Plus lambda times s. Okay. So the reason is that in some sense the norm of x1 can be written as a sum of I from 1 to n, and each individual coordinate is max of xi comma minus xi. Okay. So the absolute value of xi can be written as the max of xi comma minus xi. Right? So again, we use the fact that we can take the convex hull. Since this is a max, for each case we can take the convex hull of this, and at each coordinate the subgradient basically now belongs to minus 1 comma 1, right? Because this is the convex hull of this. Okay. Any questions until now? So that's why the subgradient of this function is x minus y plus lambda times s, right? Where s is the sign if x not equal to 0, and Si belongs to -1 comma 1 if Xi is 0. Okay. So typically when you're implementing this in an optimization problem, right, you would use one of the values of Si for the subgradient. So for example, if Xi is equal to 0, typically you just use Si equal to 0, right? Because 0 just lies in between -1 and +1, so you just use 0 when you're doing L1 regularized, say, linear regression, right, or L1 regularized logistic regression. So this is what you would use in practice. Okay. Okay. So finally, we look at the property of local minima and kind of now connect this to properties of convex, kind of minima of convex functions, right? So in general, a function could have several local minima and local maxima, right? So a definition of local minima. So what's a local minima, right? So local minima is of function f, is a point. So x is a local minima of f if there exists an epsilon such that in the neighborhood of this epsilon, right? So neighborhood is nothing but the norm of x minus z less than epsilon, then f of z is greater than or equal to f of x. Okay, so what this means is that you take a point over here, right, which is x, you take a small local neighborhood of epsilon, right, and you take basically any z in this neighborhood, right? So here we have that f of z in this neighborhood will be greater than or equal to f of x, right? So imagine you have a function that goes something like this. This point is a local minima because I look at the neighborhood, then this is basically going to be lesser than everything else in the neighborhood, right? But it's not a global minima, right? Because you could have maybe this point being the global minima. Okay, so this is the difference between local minima and global minima. So this is the local minima, and maybe in this function this is the global minima. The reason why we are characterizing local minima and global minima is because, as we will see, gradient descent style algorithms actually will converge to a local minima. So you cannot guarantee in general global minima convergence, right? So that's one of the limitations of this. And in some sense, for deep learning, which are non-convex, you could have multiple kind of local minima, right? And possibly those may not be the global minima. But in the case of convex functions, it holds that actually a local minima is going to be a global minima, right? So we'll actually see this soon, right? But before that, we'll just kind of bring one more connection. So if a function f is differentiable, right, and x is a local minima, then the gradient of f of x is actually equal to 0. Okay, but if f is non-differentiable, then we could have basically local minima with non-zero subgradients. Right? So an example of this is again x1, x2 in basically as a norm of x1 minus x2. Right? So f of x1, x2 is the absolute value of x1 minus x2, right? And again, at the point 0, right, which is a local minima, you could have non-zero subgradients. But in the case of non-differentiable functions, the condition that we require then is that 0 should belong to the subdifferential. Okay, so we could have other non-zero subgradients, but there should be at least one subgradient in this subdifferential which is exactly 0. Right? So 0 must be a valid subgradient. So is the converse true? So just because f of x is equal to 0, then is it a local minima? So it turns out no. So there could be actually points which have 0 gradients, but they are not actually local minima, right? And such points are called saddle points. So if you look at x1 square minus x2 square, right, then this function, so sorry, this is a two-dimensional function, so it's not going to be possible to plot this, but this function basically essentially it kind of goes up and down like this. So it looks like a saddle, so that's why it's called a saddle point. Yeah, so this is for local maxima as well. So the same intuition holds. Yeah. Any other questions? Okay. So now we will actually prove two very important and fundamental kind of characterizations of convexity and global minima, right? So any point of any point which is a local minimum point is also a global minimum, right? So for a convex functions, local minima is the first point, implies global minima. And what I'll do is I'll give a sketch of the proof here in class, and you can again kind of read the slides in more detail for the full proof. The second result says that if the function is strictly convex, then there is a unique global minima, equality local minima, right? So these are the two main results that we will actually show. So the first theorem is that if f is convex, right, any point which is a local minimum solution is also a global minimum solution, right? So here we assume that x, so to basically prove this, we assume that there exists a x which is a local minimum, there exists a y which is a global minimum, right? But assuming the contradiction, right, that assuming that there exists a global minima which is not the same as sorry. So there exists a local minima which is not a global minima. What that means is that there must be some other point which is a global minima which is less than this local minima, right? So essentially, that's what this is saying, that there exists a y in D such that f of y is less than equal to f of x, right? So again, x here is the um, x here is a local minima, right? And y is the global minima, right? So now the way the proof of this works is that since x corresponds to local minima, you can take a neighborhood around x, right? So you can set a epsilon around x such that this is true, right? So for any neighborhood z close to x, f of z is greater than or equal to f of x. Okay. Now what you do is that you actually define a very specific z where the theta is defined kind of very kind of smartly in this way, right? So you define theta um, to be epsilon divided by 2 of the norm of y minus x square. Okay. So then you basically kind of show that this point is a local minima, right? So that means that f of y also is less than or equal to f of x. Okay, and uh, then you essentially set this z minus x to be epsilon by 2, and finally, right? So you basically need to go through a step of points, steps, right? A set of steps, and finally, what you will arrive at is that you will arrive at the fact that f of z is less than or equal to theta f of x plus 1 minus theta times f of y. And now, since you have that f of y is strictly less than f of x, again, recall that y was our global minima, right? And x is just a local minima. So because this is true, you have now theta times f of x plus 1 minus theta times f of y is strictly less than f of x. Okay. So essentially what this implies is that f of z is strictly less than f of x, right? So we start, so if you recall in the proof, we start with a point z which is in the neighborhood of x, right? Which is going to be greater than or equal to x because it's a global minima, right? And then you derive a set of points by connecting it to y, and finally you achieve that f of z is actually less than or equal to f of x. Yes, Professor.
You are slightly better off by assuming that y is a point where fy is less than fx, not necessarily the global minimum, because global minimum may not exist. And your proof would be stronger.
Yes, that's a good point. That's a good point. So essentially what you are saying is that you're essentially kind of talking about a hypothetical function that looks like this, that continues going down,
Correct.
right, forever, and there may not be a global minimum. Actually, that's a great catch. Thank you, Professor. It's great. So actually, it's good to have someone wise in the class to kind of point these things out. But yeah, I think this makes sense, right? So essentially, so for this proof, all that suffices is that there exists a y in the domain, right, such that f of y is strictly less than f of x, right? And this is all that is used in this proof, right? And then you basically again derive the set of points and finally set of steps, and finally you will come come to this condition that f of z is strictly less than f of x, right? Which contradicts our point of local minima. Right? So this is the way you would prove. Again, I'm spending some time going over these proof sketches so that you can learn how to think about these proofs, right? I think that's the main part of this advanced course, because like all of you are PhD students. Um, so you kind of can learn how to show these results. Okay, so next, the proof of this is actually a bit easier, which shows that that for a strictly convex function, so if you have a strictly convex function, right, then f has a unique global minima, right? So to show this, all you need to basically do is that you take x in the domain and y in domain, right? Such that y is not equal to x, so that there are two global minima, right? And now you have that f of x is equal to f of y, right? So now you take this point x plus y by 2, which is in the center of the two, right? And then you essentially use the strict convexity, right? So the strict convexity essentially is that f of x plus y by 2 is strictly less than f of x plus half of f of x plus half less f of y, right? And now since f of x is equal to f of y, this is nothing but f of x, right? So this contradicts the fact that x and y are both global minima, because now you have something which is x plus y by 2, which is in between the two, which is strictly lesser than f of x. Okay? So what this means is that there cannot really be two distinct points which are both identical in value and are both global minima. Okay? So again, this is one of the nice um, properties of um, convex functions. Yeah, so there may be none. Yeah, that's actually a good point. So if there exists a global minima in a domain, right, then the global minima would actually be unique, right, for strictly convex functions. And typically, to actually kind of subvert this, what is done in practice is that you assume that your domain actually is bounded when you're doing optimization, right? And in that case, you are basically doing it in this constrained environment, and then your optimum would be somewhere in the boundary, right? But actually, that's a great point. There can be scenarios where, actually, maybe I'll just add this as a kind of a correction here, that uh, if there exists one. So if there exists minima, then this then it must be unique. Okay. So in fact, this is exactly what what I have a slide for, over here next. So does global minima always exist? So not necessarily. So even if the function f is bounded from below, right? So for example, f of x is equal to e raised to x. It may not actually, you may not be able to find a x which exactly is the global minimum, right? So even though over here basically e of x is always greater than or equal to 0, right? It achieves this point at minus infinity, right? So so basically this result, which is Weierstrass theorem, I think, shows that if f is a convex function, and suppose that there is a non-empty and bounded sublevel set, right, then f has a global minima, right? So in some sense, this shows it through the existence of bounded sublevel sets. So again, there are some details over here. I'll actually skip this in the interest of time, but you can kind of go over a lot of this in more detail. And actually, a lot of this actually I'd like to acknowledge. I use slides from a convex optimization course in ETH Zurich. I forget the name of the professor. He actually has a book which actually built a lot of this and the 2.2 lecture. So I'll point out to those slides and that book as well in the GitHub page, right? So you can kind of read through this for more detail. Okay, so the next interesting result shows that the critical points of convex functions are going to be global minima, right? So essentially what this means is that if the function f is convex and differentiable, right, then if the gradient of f at x is equal to 0, that is, it's a critical point, then x is a global minima, right? So the proof of this actually is very, very simple. So all you need is that suppose the gradient of f of x is equal to 0, right? Then just using the first order characterization, you can see that f of y is greater than or equal to f of x plus gradient of f of x transpose y minus x, and this is greater than or equal to f of x, right? But because now the gradient of f of x is equal to 0, this is greater than or equal to f of x, right? For all x. So that means that x itself is a global minima. Unfortunately, this result cannot be extended to non-differentiable functions, right? Because and the main reason is the global minima may not be at a differentiable point. And the other thing to keep in mind is that there are no saddle points for convex functions. Okay, so with this now we can kind of come up and kind of bring up the kind of standard convex optimization problem, right? So uh, and essentially this is important because there are two important things over here. Okay, so you are minimizing. So actually this should be a W. So you are minimizing. This is the X. So sorry, this is a typo. So W here is the optimization variable, and this may not necessarily be a scalar. It could be a vector, right? Or in fact, it could be multiple variables all concatenated together, right? Finally into a vector. And the problem then is to minimize f of w subject to w being in x, right? So now in a kind of a quintessential convex optimization problem, we have f as a convex function, right? And the set x as a convex set, right? And obviously w is the optimization variable. So it turns out that you can characterize this kind of rich class of optimization problems into convex optimization. And if x is nothing but the domain of f, then you don't really require anything because f itself is defined on its domain. So you can just basically say, you can kind of write this as minimum of w, f of w. This problem is called unconstrained optimization. And you also then have constrained optimization, right? So a special class or a special case of this is where f is a convex function and gi's are convex functions, and then you minimize f of w subject to gi of w less than or equal to 0 and hi of w is equal to 0. Right? So these are called inequality constraints, and these are called equality constraints. Okay. It turns out that you can also give optimality conditions for constrained optimization, right? And in the case of constrained optimization, you have the gradient of f of x star transpose x minus x star greater than or equal to 0, right? So recall that in the unconstrained case, if f is differentiable, right? Of course, here you again are assuming f being differentiable. So if f is differentiable, then you have this equal to 0, right? So this may not hold necessarily in the constrained optimization case, because the point where you have the 0 subgradient may not actually belong to the x, the set x, right? So you're searching over a set which does not have the global minima of f everywhere, right? So in that case, what will typically happen is that the minima would actually belong to one of the boundaries of the set x, right? And in some sense, this is the more general optimality, kind of the optimality condition, right? Which says that the gradient of f transpose x minus x star is greater than or equal to 0 for all x in capital X, right? And again, this is a nice geometric interpretation of this optimality condition. Okay. Two important special cases of this. The first one is a linear program where you minimize C transpose X subject to AX less than or equal to B. And the second one is a quadratic program where you minimize half X transpose QX subject to AX less than or equal to B. Right? So these are again inequality constraints, and my function f of X is either a linear function or it's a quadratic function. Okay. Okay, so with this, we actually end the 2.1. So we have kind of now studied convexity and again different properties of convexity, optimality conditions, and properties of convex functions, as well as uh, kind of properties on the global and local minima of convex functions, right? So with this, now we can actually move now to gradient descent and family. I'd like to mention that this part is going to be slightly long and again slightly kind of more involved. So what I plan to do is I plan to cover some of the proofs only today, and I'll be recording one more extra lecture where I'll actually go over all the proofs in detail. Right. So maybe I'll go over the first proof in detail and then I'll skim through the other proofs very quickly. But what I'll do is I'll actually kind of have an extra lecture where all the proofs are there in detail so that you can kind of listen to this offline. But I won't spend the time of the class in this. Okay. What we'll do is we'll take maybe a 3-minute break, like last time, and we'll start at maybe 1:30, 1:36, right? So it's 1:33, I believe, right now on my clock. So we'll start in 3 minutes, and we'll start with lecture 2.2. Okay, so we'll give a minute more, but I just wanted to see if are there any questions um, on lecture 2.1? Yes, Nathan.
Can you? I just wanted to make sure I wrote down the definition for the minimizer correctly. It's like the second to last slide.
This one?
Yes. Okay. Okay. Yeah. Thank you.
Yeah, no problem. Okay, so actually maybe I'll just mention this one thing since you kind of brought this up, right? So note that this subsumes, so actually there are two cases over here, right? The first case is if there exists a x star, right, in the set x such that gradient of f of x star is equal to 0, right? So what this means is that imagine that you have a function like this, right, and say my set x is this, right? That means that there is the global minima that belongs to this, right? So in that case, again, this property still holds because for all x, for x star, this dot product is greater than or equal to 0. In fact, it is 0, right? Because the gradient of f exactly is 0. Okay. But the second case is that there doesn't exist x star such that the gradient is equal to 0, right? In which case, as I said, that it would belong to one of the boundary points, right? So in that case, what this intuition, what this basically says is that now you take any point x within this set, right, and you take x minus x star, the gradient should be basically in the same direction, right? So essentially, the dot product between this should be greater than or equal to 0. So that will be yes. Was there a question? Okay, sorry. Okay, yeah. So again, this is kind of this nice geometric interpretation that you have these two cases, and this optimality condition kind of subsumes both these cases. Okay. All right. So again, in this part, we will actually study some of the proofs of gradient descent, right? And particularly, we will look at three specific results. We look at the convergence results of gradient descent in the case of continuous functions, smooth functions, and strongly convex functions, right? And various combinations of them. Unfortunately, what we won't have time for today, but we'll do this in week 3, is study the Nestro's accelerated gradient descent, lower bounds of these, as well as things like projected gradient descent, proximal gradient descent for constraint problems, right? So actually, I'll actually acknowledge that some of these slides were taken from Martin Juggy. So actually, I couldn't remember his name earlier, but so he has actually a nice course in EPFL, and also he has a book on some of the techniques. And secondly, I also used Sebastian Bubek's Foundations and Trends in Machine Learning book. So I will actually post all of these books on the GitHub page, right? So I've basically used the kind of these two sources for coming up with the slides and the results. Okay, but hopefully, I actually found that amongst a lot of different proofs of this, in some sense, the way it was described by Martin Jaggi was kind of very intuitive, and I use the same structure, and hopefully the proofs are actually kind of more straightforward now. So even for a long time, I was always searching for a kind of very nice and simple way of proving the convergence results of various gradient descent algorithms, right? And I think that kind of these proofs are nice, but again, they're a little bit more involved. So as you can see, there are like 173 pages here, so this is obviously going to be long. So that's why I'll kind of skim through most of the proofs, but I'll have a more detailed lecture put up. Okay. Okay, so we'll kind of recap now and actually define one more quantity called the Lipschitz continuity. So we have not actually studied this quantity. So the Lipschitz continuity is basically a constant that kind of says how much does the function change with respect to a linear function, right, or just x minus y. So essentially what this says is that f is Lipschitz continuous, right, with a Lipschitz constant L if the absolute value of fx minus fy is bounded by L times the norm of x minus y, right? And again, over here, x and y are vectors in R raised to b. Okay, so essentially Lipschitz continuity limits how fast the function changes. Okay, so another way to kind of write this is that Lipschitz continuity implies that for any x in the domain of f, the subgradient h belonging to del fx satisfies that the subgradient is less than or equal to L. Okay, so this is fairly restrictive, right? And like as you can imagine, a lot of functions that grow much faster than a linear function would not satisfy this Lipschitz continuity, right? So what is oftentimes done again is that these functions are analyzed in scenarios of bounded domain, right? So you imagine, you basically assume that the x, which typically is like the weight function, right, or the weights, that the x is like bounded somehow. And if x is bounded, then you can actually show that the Lipschitz continuity, that this is still true, right? So you can basically give a Lipschitz continuity term. So properties of Lipschitz continuity are that if f1 is L1 Lipschitz continuous and if f2 is L2 Lipschitz continuous, then f1 plus f2 is L1 plus L2 Lipschitz continuous. Right? So again, I'm not proving this, but you can prove this relatively easily actually. It turns out that the product of two Lipschitz continuous and bounded functions are also Lipschitz continuous. Okay, so now we'll also define this quantity called smooth functions, right? So a function f is smooth if its gradient is Lipschitz continuous, right? So a Lipschitz continuous function is if the function itself is Lipschitz continuous. Here we are saying that a function f is smooth if the gradient of this function is Lipschitz continuous. Okay. So what this means is that the gradient of f minus the gradient of the gradient of f at x minus the gradient of f at y is less than or equal to L times x minus y. Right? So what it means is that the gradient of f does not grow too fast. Right? In turn, this implies that the Hessian matrix of f is less than or equal to, from a positive semi-definite sense, right? L of I, right? So in other words, this means that the Hessian minus L of I is actually negative semi-definite. Right? So this is negative semi-definite. Okay, so interestingly, what this basically kind of proves now is that if a function f is smooth, that is, it has Lipschitz continuous gradients, then we actually have a quadratic upper bound on f. Okay, so this means that f of y is less than or equal to f of x plus the gradient of f of x transpose y minus x plus L by 2 y minus x square. Okay, so I'll kind of contrast this with strong convexity soon. So again, you must be thinking about strong convexity. In the case of strong convexity, we had a lower bound, right? So strong convexity was that the function is lower bounded by a quadratic function. Lipschitz continuous gradients or smoothness says that the function is upper bounded by a quadratic function, right? So basically, functions that are both Lipschitz continuous or smooth are essentially variants of quadratic functions. So they are quadratic functions plus other smooth functions, right? So we'll actually come to this also in the next few slides, right? So let's consider obviously f of x equal to x square. This function is definitely going to be Lipschitz continuous because this is kind of a quadratic function. So here we have that any L greater than or equal to 2 would basically, this would be Lipschitz continuous with any L greater than or equal to 2, right? So sorry, this is Lipschitz smooth. So fx equal to x square is Lipschitz smooth. What about fx raised to x, fx equal to x raised to 4? Is this Lipschitz smooth? What do you guys think? Is x raised to 4 going to be Lipschitz smooth? Any thoughts? Okay, why? Yeah, so actually x raised to 4 is not Lipschitz smooth, right? So okay, so maybe I'll just recap over here a little bit, right? What Lipschitz smoothness says is that the function grows at most quadratically, right? So that means that f of y is actually less than equal to f of x plus this term plus some quadratic term, right? So anything that grows faster than quadratic is not going to be Lipschitz smooth. Okay, but another way to view this is just from the definition itself, right? So take the gradient of this term which is 4x cube, right, minus 4y cube, right, and take the, so there should be, so basically take just the absolute value of this, right? Exactly, right? So this is going to be equal to 4 times x minus y, right, multiplied by x square plus y square plus xy. If assuming I remember the, assuming I remember the, I don't know, I don't remember there's a plus sign or a minus sign here. Can someone remind me? I think there's a plus sign, right? But I think what, so essentially whatever be the point, right? So the point is that here this term itself grows quadratically, right? So you can't pick any L which is a constant such that this would be less than equal to L times x minus y, right? Of course, you could probably do this if you assume that your x is bounded, right? So if your x is bounded, then you can kind of trivially come up with an upper bound of this quantity, right? And then you can show some kind of a Lipschitz smoothness in this restricted set, right? But in general, everywhere it is not Lipschitz. Okay. So in fact, this is a proof that even x cubed by 3 is not Lipschitz smooth. Right? So you take x cubed by 3, then the gradient is x squared, right? So you have x squared minus y squared, and this implies that x plus y is less than equal to L, right? So this is not true globally. Okay, so what this means, I think this is the critical thing, right? So only functions that are asymptotically at most quadratic in growth can be Lipschitz smooth globally, right? Okay, so then maybe we'll take one more example very quickly, right? So take this function where which is like f prime x is equal to the absolute value of x, right? So you have this from Lipschitz smoothness, right? And the absolute value is actually Lipschitz continuous, right? So it's not Lipschitz smooth, sorry, Lipschitz. Okay, but this function is actually not differentiable everywhere, right? In fact, it's not differentiable at 0, right? And So the question then is also okay. So we saw that functions that so Lipschitz smoothness function should at least be kind of quadratic, at most quadratic, right? But the question is every subquadratic function Lipschitz smooth, right? So it turns out that no, because you require kind of little bit more than that, right? So you require also that the gradient should exist. So you require the function should be differentiable. So there can be kind of subquadratic functions that are not differentiable, and these functions will not be Lipschitz. Right? So that's what this slide is saying. Right? So in some sense, Lipschitz continuous and Lipschitz smoothness kind of relate also to differentiability. Right? So in fact, this is a nice relationship. I'm not going to prove it, but I think this would be kind of interesting to know in terms of a connection between different classes of functions. Okay. So the class of functions where f is continuous, right, is a larger set compared to the class of functions where f is differentiable almost everywhere, right, which is equal to Lipschitz continuity. So Lipschitz continuity means f is differentiable almost everywhere. There can be some points where it's not differentiable, right? Um, but in turn, this is actually kind of smaller than the set of points where f is continuously differentiable, right? Sorry, this is larger than the set of points where f is continuously differentiable. So basically, what we are going is we are going into smaller and smaller subsets now, and finally you have the case of smoothness, which is equal to the gradient of f being differentiable everywhere, right? So essentially, to kind of summarize, what this means is that you have a larger set, which is f being continuous, right? And a smaller set is um, f is differentiable, right? And an even smaller set is f is smooth. So f being smooth requires that the gradient of f is differentiable, right? And that is equal to f being smooth. Okay, so again, Lipschitz continuity just means that the norm of the subgradients is bounded, right? So again, so if you're more interested on kind of Lipschitz continuity and Lipschitz smoothness, you can basically kind of see some of these resources. I think this, again, these slides will be there on GitHub, so you can see this in more detail. Okay, are there any questions until now? Yes, Nathan.
So I had a question about some of the equalities and the more specific subsets that we just discussed. So yes, I'm mainly concerned with why it's equivalent that if f is differentiable almost everywhere, that means it's the exact same as f being Lipschitz continuous. Couldn't you have f that is differentiable everywhere, but it's also Lipschitz continuous?
Yes, so basically f f being differentiable everywhere is a subset of f is differentiable almost everywhere, right? So Lipschitz continuity just means that f is differentiable almost everywhere, and f being differentiable everywhere also is called that f is continuously differentiable.
Okay, I think my confusion's, yeah, okay.
Right. So in some sense, the way to think about this, right, is kind of connecting the differentiability of f with notions of basically Lipschitz continuity and kind of Lipschitz smoothness as well as continuity, right? So this basically connects continuity, differentiability, Lipschitz continuity, and smoothness, right? So in some sense, the gradient. So like as you go to smaller and smaller sets, right? So f being smooth is even smaller than the set where the gradient of f is continuous. So just the gradient of f being continuous is not enough. We want the gradient of f to be differentiable almost everywhere, and that is exactly the same as, right? But smoothness is actually is larger. So like there is one more even smaller set, which is like f is continuously differentiable. Right? So this is not required for Lipschitz smoothness. So we don't have to assume that the gradient of f is differentiable everywhere. Right? All we require is that the gradient of f is differentiable almost everywhere. So again, this is slightly technical. Even if you don't understand everything, it's okay. This is not super important. I just wanted to kind of add this for FYI, right? And I think these resources would be useful if you want to kind of brush up more on Lipschitz continuity. By the way, these slides are actually there on the GitHub page now. Okay. So let's kind of contrast now strong convexity with Lipschitz continuity and smoothness, right? So recall that a function f is strongly convex if there exists a mu greater than 0, right? So this is a strong convexity coefficient. This was the same as C, what we were seeing earlier, right? Such that f of x minus mu by 2 x square is convex, right? So the question is that, is there a similar result for Lipschitz smooth functions, right? So it turns out that there is. And I'll kind of contrast this, right? So here we have, in the case of strong convexity, that f of x minus mu by 2 x square is convex. But for Lipschitz smoothness, we require that L by 2 x square minus f of x be convex, right? So in some sense, this is like a sandwich. One expression is saying that you subtract mu by 2 x square, it should still be convex. And the other one is saying that you actually subtract from a quadratic function f of x and it should still be convex, right? So in some sense, this should tell you that there is some kind of a sandwich property over here, right? So sorry. So I was actually sorry about my drawing, right? So essentially, the intuition again, we'll kind of see this intuition again, that if this is f of x, right, it means that there is a quadratic upper bound and there is a quadratic lower bound everywhere. So I think this is critical, right? For functions that are Lipschitz continuous, or sorry, Lipschitz smooth, right? You have, so this is Lipschitz smooth. You have a quadratic upper bound, right? And for strongly convex, you have a quadratic lower bound, right? So if there is a function that is both strongly convex and Lipschitz smooth, you can see that those are at most quadratic functions. Those are functions that only grow quadratically. Okay. Any questions on this? Okay. So again, there is an interesting duality between this, right? So we'll kind of connect the duality between this in a few lectures down the road. Okay. Um, so if a function f is strongly convex and g is convex, then then f plus g is strongly convex. Right? So we saw this last time. Now, if f1 is Lipschitz smooth and if f2 is Lipschitz smooth, then f1 plus f2 is also Lipschitz smooth, right? But if a function f1 is Lipschitz smooth and if f2 is just convex, right? Then it's not necessary that f1 plus f2 is also is Lipschitz smooth, right? Because unlike strong convexity, Lipschitz smoothness requires a quadratic upper bound. Okay, so there could be a convex function which is not Lipschitz smooth, which is for example strongly convex and grows more than a quadratic function, right? In which case the sum of the two would not be Lipschitz smooth anymore. So for Lipschitz smoothness, we require both f1 and f2 to be Lipschitz. Okay, so now we'll take a step back, right, and kind of think about some of the loss functions that appear in machine learning. Okay, so it turns out that the logistic loss, which is log of 1 plus exp to minus yi multiplied by theta transpose xi, this function is Lipschitz smooth. Any ideas why? Or maybe rather, how would you prove this? Yes, Nathan.
So I mean, you can, for first thing, you need to compute the gradient, and then you would take arbitrary points x and y, and then take the gradients of both of those, subtract them, and then take the norm of that. If that, for any x and y that you choose, is less than or equal to L times just the difference between x and y and the norm of that, then it would be Lipschitz smooth because it satisfies the definition.
Yes, so like, okay, so there are multiple ways of doing this, right? The way you described, you need to analytically write down basically L of, maybe I'll just write this as L of theta 1, right, minus L of theta 2, and try to find out Lipschitz smoothness. I'm calling this like script L because L is already used here, right? And it's like theta 1 minus theta 2, right? So try to show that this exists. So in some sense that the gradient of this, right? So in some sense the gradient difference grows at most linearly, right? Other way of showing this is actually to um, take the second derivative of L of theta, right, and show that this is basically less than equal to L of I, right? In some sense, it kind of suffices to just kind of argue um, the the growth of the function. So if any function grows larger than quadratic function, then this is essentially um, sorry, if it grows smaller than a quadratic function, right, then it's Lipschitz smooth, basically, right? So you can use either of these proof techniques to show that this is Lipschitz smooth. But basically, logistic loss is Lipschitz smooth. It turns out that the hinge, okay, so the hinge loss is not um, Lipschitz smooth because it's not differentiable, right? But it is Lipschitz continuous because you can actually compute the subgradients and you can get bounded subgradients. right? The other function is the multi-class logistic regression, right? So again, because kind of similar to logistic regression, this function is Lipschitz smooth. Then the least squares function is actually Lipschitz smooth and strongly convex because it is growing quadratically, right? So that's why it is both. And finally, when you add a L2 regularization, right, then you essentially get strong convexity. So for example, if you add L2 regularization to logistic loss, then you make the function both Lipschitz smooth and strongly convex. Okay, so essentially L theta plus theta square. This is going to be Lipschitz smooth and strongly convex. Yes, Nathan.
I just want to make sure the L2 regularization also depends on the loss not growing asymptotically larger than the quadratic function, right? Like say
Yes, yes. Yeah. So basically, L2 regularization itself is Lipschitz smooth and strongly convex. So basically, what I mean here is that this function, right? This is Lipschitz smooth and strongly convex, right? But obviously, when you add it to another function, then it is not going to be, not necessarily going to be Lipschitz smooth anymore. Actually, we will come to this. So L1 regularization is Lipschitz continuous. Okay, again, it's not going to be smooth. So now, so maybe I'll just come through all the slides here very quickly, right? So I think this part is fairly easy. So you can kind of now combine functions and argue about these properties, right? So for example, L1 regularized logistic loss is Lipschitz continuous. L2 regularized logistic loss is going to be strongly convex and Lipschitz smooth, right? Because logistic loss itself is Lipschitz smooth, right? And L2 regularization is also Lipschitz smooth, right? So the sum of them is going to be Lipschitz smooth. And since one of them is strongly convex, the L2 regularized one is strongly convex. Okay. L1 regularized hinge loss is Lipschitz continuous. L2 regularized hinge loss. This is interesting, right? So it's Lipschitz continuous, but it is also strongly convex. So the Lipschitz continuity of this actually there's a caveat. So this is Lipschitz continuous only on a bounded set. Okay, because again, the subgradient of, since you have the theta square, right? The subgradient of this, or the gradient of this, which is theta, right, is not necessarily bounded everywhere. But if you assume that theta is bounded, so the norm of theta is bounded by b, right? This implies that the subgradient of this function, right, is bounded by b, right, which shows that this is going to be strongly convex. Any questions on this? Yes, Saurabh.
Professor, so how would the bounds on theta, uh, I guess, affect the optimization algorithm, or how would that show up in a, I guess, um, algorithm? How would we implement
Yeah,
that?
that's a good question. So it doesn't come up in the algorithm per se, right? But these are additional assumptions that are made so that a convergence bound can be shown. So in many of the convergence bounds that we'll see, it is standard to assume that the parameters are bounded. Okay, and this boundedness of the parameters is required in order to have conditions like Lipschitz continuity, for example. So for example, Lipschitz continuity is going to be useful in showing a convergence bound, right? And for that bound to hold, we will have to assume that the parameters are bound. So it's not going to be a specific to the algorithm. So the algorithm is not going to magically make sure that that's the case, but you can argue that for certain loss functions, when you add a regularizer, right, you don't get too crazy of loss values, right? So that's the point of regularization. So regularization will ensure that the theta parameters are not crazy, right? So they are still bounded somehow, right? And that somehow is going to be useful in the analysis. Does that answer your question? So the algorithm is not going to do anything specific. So to basically give a short answer, right? It's going to be an assumption in the analysis. Yeah.
I see. Okay.
Okay. So So L2 regularized least squares is also Lipschitz smooth and strongly convex, and L1 regularized least set is also Lipschitz continuous and strongly convex. This is again going to be on a bounded set. Again, we require bounded set because we want to have Lipschitz continuity here. Okay, so with this now, we will start looking at gradient descent. So it looks like we have around 40 odd minutes, right? So uh, what I'll do is I will try to describe the main results for different settings, right, and prove only the result in one of the cases, right, and the other ones I'll just kind of go through the proof very quickly. So does these bounds also help in the guarantees of sample complexity? So these are not really. So these results are going to be convergence results, okay? And that's what I'm going to describe what these convergence results are. So these are not really related to sample complexity bounds, like how we see in learning theory. That requires different machinery. All we are going to guarantee is that the optimization algorithm works. Okay, so maybe I'll spend some time on this. So within machine learning, right, there are two kinds of bounds or like two kinds of theoretical results, right? One is the optimization related and the other is statistical. So the statistical is oftentimes model related, right? And the optimization is like loss functions related or like optimization algorithm. Okay. So what the statistical one will assume that, it will assume that you can somehow get the global minima, right? And assuming that you can get the global minima, it will tell you how many samples are required for showing a certain kind of guarantee, right? So the statistical part is going to be like number of samples required for the generalization bound, right? Whereas the optimization one is going to say that what are the number of iterations in the algorithm, right, to achieve close to theta star. Okay. So in some sense, both of these will be connected, right? So we want to have both. We want to have both statistical guarantees related to our model, which says that the model is somehow not too complicated, right? So that I can show a generalization bound, but I also want to make sure that my optimization itself works. Okay, does that answer your question? So we are going to focus in this entire course mainly on this portion. Okay, so this is going to be the focus. So what does it mean, right? It means that now can we find a x in r raised to n such that my f of x minus f of x star is less than equal to epsilon, right? So most of the algorithms are going to be iterative algorithms, right? So what I mean by iterative algorithms is that we initialize the x0 to be randomly, right, or say to be 0, right? And then we are going to do this iterative algorithm as xp plus 1 is equal to xp minus this learning rate or a step size, right? So the gamma here is a step size parameter. This is also called, by the way, learning rate, right? And that's it. That's all what gradient descent does. Again, this is also called batch or this is also called full gradient descent. And this is to kind of differentiate between what is used in machine learning as a stochastic gradient descent. So we will talk about stochastic gradient descent algorithm variants, okay, but we won't be kind of analyzing it right now. Right now we'll be focusing on and assuming that we have access to the full gradient. So the main question is that if we have an iterative algorithm like this, right, how much time, right, or in other words, what are the
Can you guys hear me?
Yes.
Okay, yeah, sorry about that. There was a technical issue with with the with my mic and my headphones. The battery went off, so I'm just using the standard speaker. Okay, so let me just share my screen again. Sorry about that. Okay, can you see my screen? Yeah, okay, awesome. So, all right. So the critical question is that what is the number of iterations that are required, right? So that we can reach an epsilon approximate solution, okay? Here we'll use some notation. So we'll define X star to be the global minimizer of F, right? To start the so basically in this results, right, we look at different properties of F. So we assume, for example, that if F is Lipschitz continuous, then we say it is Lipschitz continuous with the parameter B, right? And if it is smooth, if F is smooth, we'll say that the gradient F is Lipschitz continuous with the parameter L. Okay, or we'll just say that F is Lipschitz smooth with a parameter L. Okay, so B is going to be the Lipschitz continuity parameter of F, and L is going to be the Lipschitz smoothness parameter of F, right? So, so suppose a function is Lipschitz smooth, then we won't use the Lipschitz continuity because Lipschitz smoothness is somehow stronger, right? It will help us give better bounds. But if it is not Lipschitz smooth, then we'll try to use Lipschitz continuity, right? And one more parameter we'll use is strong convexity. So strong convexity we'll say is mu, right? So this is strong convexity. Okay. So again, I'll be using like a lot of this course content from Martin Jaggi. So this is an illustration of gradient descent, right? So I start over here with x1, right? And I go to x2, right? I go to x3, I go to x4, and so on and so forth. And finally, after a few iterations, hopefully I converge to the global minima, right? The question is, can we theoretically guarantee the number of iterations required for gradient descent to converge, right? So it turns out that the answer is yes. And you know, this actually holds because of kind of nice properties of convexity, right? So I will carefully go over the first result, which is the result for Lipschitz continuity, and kind of build through the proof in the next few slides. And then what I'll do is I'll quickly then go through I'll just skim through the rest of the results quickly. Okay. So define GT to be the gradient of F at xt, right? So now from the definition of gradient descent, we have that the gradient of at t of xt multiplied by xt minus x square is equal to this, right? Why is this the case? Because the gradient is nothing but, or actually gamma times the gradient is nothing but xt minus xt plus 1, right? Why is this? Because xt plus 1 is actually defined as xt minus gradient times gt, right? So this is nothing but gradient descent. Okay. Any questions on this? So this part is clear, right? So now what we use is we use this fact that 2 times v transpose, sorry, just give me 1 minute. Yeah, okay. So 2 times v transpose times w is equal to v square plus w square minus v minus w the whole square, okay? So we'll use this fact in actually expanding upon this term. So we expand out this term as half times gamma. So we take, so okay, so we actually expand the RHS of this, sorry, right? So we expand this as by taking half times gamma, right, multiplied by xt minus xt plus 1 the whole square plus xt minus x star the whole square minus xt plus 1 minus x star the whole square, right? Why is this? Because again here I'm substituting v and I'm substituting this as w, and v transpose w is equal to half times norm of v square plus norm of w square. Yeah, sorry, was there a question? Okay, minus norm of v minus w the whole square, right? So that's exactly what this is. Okay, so So basically this is the bracket over here, and then then all I do is that I substitute back xt minus xt plus 1 is equal to 1 over gamma times, or sorry, is equal to gamma times gt, right? So I substitute this back over here when I go from this step, right, to this step. So I substitute this expression, right, and then gamma, this becomes gamma square, it gets cancelled by gamma, right? So finally I have gamma by 2 gt square, okay? And finally this expression is the same, okay? Is this clear? Or are there any questions? Please stop me if there are any questions, okay? Okay, so far I have this, right? So I have the right hand side here, which is gt transpose xt minus x star, which is equal to this term, which is gamma by 2 gt square plus 1 over 2 gamma and the difference between these two, right? So now what I do is that I sum this over, right? So last time we had this expression, right? So this was what we derived until last time. And then summing this over now, we sum this over for t iterations, right? So we get this expression basically, which is the right hand side, right? Which comes by just summing over this, right? Is equal to gamma by 2 gt square, right? Plus, so now this term, okay, this term actually gets telescopically cancelled because I'm taking a sum over t iterations. What's happening is that there is this t minus t plus 1, right? In the next time there is t plus 1 and t plus 2. That's why t plus 1 here will get cancelled with this t plus 1, right? So there is a telescopic sum that occurs, and finally all I'm left with is this expression here, which is half gamma multiplied by x0 minus x star the whole square minus xt minus x star the whole square. So basically the first term, which is x0, and the last term, which is xt, right? So I'm summing this over actually for capital T iterations, right? So that's why I have this capital T here. Any questions until now? Okay. So far so good, right? So this result, I'll just recap this result. So this result is nothing but the sum of t equal to 1 to t minus 1 gt transpose xt minus x star is equal to gamma by 2 and the sum over the gradients plus 1 over 2 gamma, the difference between x0 minus x star minus xt minus x star. Okay. Now what we do is we invoke convexity. Okay. So here I have this gt transpose x xt minus x star, right? So this is very reminiscent of the first order convexity kind of upper bound, right? So we have that f of xt minus f of x star is less than equal to this expression, right? So what this means is that I have this from the previous slide, which is gt transpose xt minus x star is equal to this, right? And now combining with this fact, right? Okay, so actually before this, what I do is I kind of subtract, I actually remove out this term, right? Because this term is actually greater than or equal to 0, right? So now I have something minus something which is positive, right? So what this means is that this expression will be less than or equal to this term. Okay, so that's what I have over here. And finally, I will actually use this upper bound. So I will further make this kind of, I will add this over here, right, as fxt minus f of x star less than or equal to this, and then I have a sum over t. Okay, so that's exactly what I have over here. So I have this sum over t of f of xt minus f of x star is less than or equal to, and I'm left with these two terms. One is gamma by 2 gradient square plus 1 over 2 gamma times this difference between x0 minus x star. Okay, so then what I do is that I can assume that x0 minus x star is bounded. So again, this is where we will be using the assumption that the weights and the parameters are bounded, right? So we assume that this term, that actually for any x in the domain, the norm of x is less than or equal to r. And this assumption, as I was saying, is not too crazy, right? Because for most machine learning applications, or actually kind of most applications, you are dealing with bounded scenarios. From a theoretical mathematical perspective, it makes sense to do unbounded scenarios, right? But from a kind of more, again, from a more engineering or a kind of a application perspective, you will not very oftentimes have unbounded x's, right? So you can assume without loss of generality that your x is bounded. And then we also assume that the gradient of f is bounded, right? Again, this is something that can be shown for most loss functions. So then we set gamma to be r divided by b times square root t, right? So r is this bound on parameters, and b is the Lipschitz continuity. Okay. So combining with these two, what we will have is we will have that the sum over t f of xt minus f of x star is less than or equal to rb multiplied by square root t. Okay, so this is an average. So this bound is showing that the average over all iterations is bounded, right? But what you can also show is that you can also do this over the min. So note that the last iterate is not necessarily the best, because we have not anywhere shown right now that we can reduce the objective value, right? So gradient descent does not necessarily yet reduce the objective value if we just assume Lipschitz continuity. So we assume that x hat is equal to the arg min, right? And basically then it's easy to show that now my f of x hat minus f of x star actually satisfies this bound, which is rb over square root. Okay. Any questions until now? Is this part clear? Even though the proof is not fully clear, is the intuition clear what's going on? I will give some more intuition of what this bound exactly means and what can be derived with respect to t, but so far are things clear? Any questions? Okay. Okay. So now we'll actually derive the final bound, right? So define x hat to be argmin of I, f of xi, right? Then we have that the absolute value of f of x hat minus f of x star is bounded by rb over square root t. Okay, this is what we discussed from last time. Now this is where epsilon comes in, and again this is very similar to the sample complexity bound that we showed in the case of generalization bounds, because there we will be there we discussed about the generalization error being less than epsilon, right? But here this is the suboptimality bound, right? So we are saying that I have my x hat which is close to x star by at least epsilon, right? And if this holds, then what this means is that rb divided by square root t is less than or equal to epsilon, right? So as long as I have a t such that rb divided by square root t is less than or equal to epsilon, this implies that this will be less than or equal to epsilon, right? So the question is, what is t? What t satisfies the above? Okay. And now you can kind of, from this you can obtain that t must be greater than or equal to r square b square over epsilon square. Okay, so this is called order 1 over epsilon square convergence, right? And so this is a final result, right? So given a Lipschitz continuous function f, then gradient descent with a constant step size of gamma equal to rb over square root t achieves a solution x hat such that this is true. Okay, so one caveat to keep in mind, that in practice no one actually computes this gamma, right? From the theoretical perspective, people just do a grid search over gamma or maybe a line search, right? But very often you don't really compute this gamma kind of theoretically, because kind of computing these quantities is difficult. And secondly, this bound is actually slightly pessimistic. So oftentimes in practice, you can see slightly faster convergence than this. So so it's not encouraged to use this in practice. But what still this shows is that theoretically we can prove that in these number of iterations you are guaranteed to get a solution, whatever be the function. As long as the function is Lipschitz continuous and you have bounded gradients and the x's are bounded, you can prove this convergence result. Okay? So I think this result actually is very strong because of this fact. Okay. So the advantage of this bound is that this gets to 0 as t becomes large, and something which is very important is that it is independent of the dimension. So there is no dependency in the dimensionality of x, where x belongs to r raised to t. So from a computation perspective, it depends on a dimension because computing the gradient requires d, right? But the number of iterations does not depend on the gradient, the dimension, right? So what this means is that you can have very high dimensional problems and the number of iterations is still the same. Okay. The disadvantage with this result is that it has slow convergence. So to achieve an epsilon error of 0.01, you require 10 raised to 4 multiplied by r square b square iterations. Okay. And this is just to and to achieve an error of 10 raised to minus 4, you require 10 raised to 8 multiplied by r square b square. Okay, so this basically is called actually kind of quadratic. Sorry, what is it called? So I forget what it's called, but this is called 1 over epsilon square convergence. It's very slow. Okay, so typically in practice we hope for either logarithmic convergence or we hope for kind of 1 over epsilon convergence. Okay, so the question is, what is r and b? Okay, so r and b is what I had defined earlier, right? So r is equal to the norm. So essentially we have the norm of x less than equal to r, right? So essentially x, or the parameters, is bounded. Okay, and second is that f is b Lipschitz continuous, right? So this is b. So f is b Lipschitz continuous and r is the bound on the parameters. Okay, any questions? Yeah, okay. Okay, so now we will talk about smooth functions, right? So smooth functions, again, recall is that there is a quadratic function which upper bounds my convex function everywhere, right? So bounded gradients means that the function f is Lipschitz continuous, but smoothness means the Lipschitz continuity of f, right? So again, properties of L are that if f1 till fm are smooth, then a convex combination of the functions is smooth. This is related to what we saw earlier. I'll actually skip this in the interest of time, right? So we can actually compute the Lipschitz continuity of logistic loss. Okay. So again, this is a more detailed derivation for the Lipschitz for the smooth case, which actually I will skip in the interest of time. I will be recording one more video before next week, where I'll kind of go over this derivation in more detail. But one thing I'd like to point out is that it turns out that for Lipschitz continuous functions, so basically all I've assumed, so in the first analysis or the first result, we just assumed Lipschitz continuity, right? Which in some sense is a weaker characterization. We made it slightly stronger by assuming Lipschitz smoothness. So what I mean by weaker characterization is slightly more general. Okay, I made it slightly more kind of restrained or kind of constrained by assuming Lipschitz smoothness. Okay, and Lipschitz smoothness requires kind of the function be differentiable and so on and so forth, right? And the gradient of f being like almost differentiable. So with Lipschitz smoothness, it turns out that you can show that the at every iteration of gradient descent, right, the objective value reduces. Okay, so this is key. So what this now entails us is that this entails that, you know, with thanks to smoothness, we can show this result that f of xt plus 1 is less than equal to f of xt minus something that is greater than equal to 0. So what this means is that f of xt plus 1 is guaranteed to be less than equal to f of xt. And if the gradient is greater than equal to 0 or strictly greater than 0, then in fact you are guaranteed to reduce the objective value if the norm of gt is greater than 0. Right, so this is good. So we have reducing of objective value, and this is what this is saying over here. Okay, so now we continue the analysis. I'm skipping all of this, and finally what we have is we have this result. Okay, so we have that for a Lipschitz smooth function, f of xt minus f of x star is less than equal to L divided by 2t of x0 minus x star the whole square, right? And again, we have the same assumption that we assume that the norm of x is less than equal to r, right? That this is like bounded. So this is equal to LR square by 2t. Okay. Any questions until now? Okay. So so now we continue this the similar kind of analysis, right? So to ensure that f of xt minus f of x star is less than equal to epsilon, we require that LR square by 2t should be less than equal to epsilon, right? Because then we will have that this is in turn less than equal to epsilon. Okay. So this implies that t is greater than equal to r square L over 2 epsilon. Okay. So magically now, from, if you recall, in the Lipschitz continuous case, we had t was greater than equal to, I forgot what it was, but I think it was r square over b square, or sorry, maybe it was r square b square over epsilon square, right? So we had a 1 over epsilon square convergence, which was like very slow, right? Now, because of Lipschitz smoothness and L, we are actually getting a convergence which is 1 over epsilon. So to understand this a little better, to achieve an error of 0.01, we require 50 r square L iterations instead of 10 raised to 4 r square b square. 10 raised to 4 r square b square, right? So this now is the linear convergence, or sorry, this is not called linear convergence, this is called order 1 over epsilon convergence. Okay. So the important thing here is that we need to set the step size to be equal to 1 over L, where L is a Lipschitz continuity. Okay. All right. So now we look at an even more restricted case where the function is both smooth and strongly convex. So an example of this is L2 regularized logistic regression. Right? By the way, an example of this, can someone tell me what is an example of just a smooth function? Which machine learning loss is only smooth? Anyone? Yes, Nathan. Logic loss.
Yeah, I was going to say from the examples you gave us, the logistic loss was even if you didn't have it regularized.
Exactly. So even without, so this is typically without regularization, right? So this result would hold without regularization, right? So with regularization, this becomes logistic regression. Okay. So with regularization, this becomes actually smooth plus strongly convex. So again, I'm skipping over the analysis, right? But we use like the previous results, and in fact over here we use gamma equal to 1 over L, and then we actually get even stronger convergence result. Okay, so combining with the smoothness, finally we get a result like this, that f of xt minus f of x star is less than equal to L over 2 multiplied by 1 minus mu over L raised to t multiplied by this term. Okay, so kind of writing this more clearly, we have, and this is by the way all with a final iterate. So even in the smooth case, we don't need to take the min. We can iterate and right. So here also we take the final iterate, and we have L over 2 1 minus mu by L raised to t multiplied by r square. Okay, sorry, actually I missed Saurabh's comment. So I think even mean square error would be smooth and strongly convex. Yes, thank you. So now to get an error of epsilon, right, we require L over 2 multiplied by this quantity to be greater than or equal to epsilon, right? So this implies that t is greater than or equal to L over mu log multiplied by this quantity r square L over 2 epsilon, right? So this convergence is log 1 over epsilon convergence, and actually this is called linear convergence. We'll see exactly why it is called linear convergence. Okay. But now to get an error of 0.01, we only require L over mu log 50 iterations instead of, you know, like even this case, right? Yes, Nathan.
So I just want to understand more clearly why we only have to look at the final iteration. Is it because that necessarily also would be our x hat, since for smooth cases it always reduces the objective at each iteration?
Exactly. So here, right, x hat. So smooth. So from smoothness. So using smoothness, what we have is that x hat, which is essentially r min over t of f of xt, is actually equal to f of xt. Sorry, is equal to xt. Right, because reduction in objective value. So here we show this over the last iterate, which also is kind of more appealing, right? Because that's what you expect. After doing gradient descent, you just look at the last one and that should be the best. So that is what is guaranteed for these cases. Okay. So just contrasting the bounds very quickly. Okay. So Lipschitz continuous functions was the worst case, which was r square b square over epsilon square. Lipschitz smooth functions was r square L over epsilon, right? And smooth plus strongly convex functions was log 1 over epsilon. Okay, so we look at some concrete examples. Let's assume, just give some numbers, that L and B are 10, right? R is equal to 1 and mu is equal to 1, right? Just some example numbers. So then what theoretically for 0.1 iterations, C would be, so in the just the Lipschitz continuous case, we would require 10,000 iterations. In the smooth case, we would require 50 iterations. But in the strongly convex case, we require only 8 iterations. Okay, so you can see the drastic gap between what slow convergence is and what fast convergence is, right? Make epsilon slightly smaller. Okay, this increases by a factor of 100, right? This increases by a factor of 10, so 50 becomes 500. But this increases by a constant, which is 5. That's why it's called linear convergence. Okay, I again make this slightly smaller, reduces by a factor of 10. See, this becomes even slower, right? And my smooth case becomes 5,000, but my strongly convex case becomes 18, right? So again, it increases by a factor of 5, right? So as epsilon reduces by 10, the number of iterations in the strongly convex plus smooth case only increases by an additive constant, right? So that's why it's called linear convergence. So unfortunately, strongly convex plus smooth is amongst the rarest functions, right? Only logistic regression with L2 regularization, right, and the least squares with L2 regularization, right, are belong in this category. Most other loss functions are not like this, right? Even with rectified linear, for example, excuse me, even rectified linear would not be Lipschitz continuous, right? Sorry, Lipschitz smooth. So unfortunately, this is very restrictive, but if we have this, we have very, very fast convergence, right? So this is the beauty of this kind of problems. Okay. So now the question is that for Lipschitz continuous functions, we saw very poor bounds, right? So actually, I'll end with this very quickly. So the question is that if we have, can we have both Lipschitz continuity and strong convexity, right? So unfortunately, no. In general, it is impossible to have a function that is both Lipschitz continuous and strongly convex, because they are kind of at odds with each other, right? Lipschitz continuity is saying that, you know, my gradient should be bounded, whereas strongly convex is saying that my gradient should be unbounded, right? It should, my gradient should be at least linear, or the function should grow at least quadratically. But if we assume that the parameters are bounded, which is what most of machine learning is, right? And that the gradients are upper bounded, then we can assume that the function is both Lipschitz continuous and strongly convex. Okay, so an example of this is the hinge loss plus L2 regularization, right? Similarly, another example of this is least squares plus L1 regularization, right? So both of these are Lipschitz continuous plus strongly convex, right? Another example of such functions would be if you have a joint norm, which is like L1 norm plus L2 norm, right? Plus say like logistic regression, or possibly hinge, or even least squares, right? So all of these functions then would be Lipschitz continuous plus strongly convex. Okay. Any questions until now? So in this case, we can get an improved order 1 over epsilon bound from 1 over epsilon square. So we saw that for just Lipschitz continuous, we had very slow convergence, which is 1 over epsilon square, right? But if you add a regularizer, so this is again the benefit of regularization. In machine learning, we only talk about the benefit of regularization from a generalization perspective, right? It makes the problem slightly, you know, better conditioned. It, you know, improves in generalization, reduces overfitting, etc. But it turns out magically that the same L2 regularization also helps to make the optimization slightly easier, right? So if you add regularization to hinge loss, it actually makes the convergence faster. So, okay, so again, this is the analysis of this. I will skip this. I will talk about this, you know, in the recorded lecture. So we'll skip actually most of these slides. So I'll just talk about a final result, right? So here we have a weighted, so this is a weight, okay? So there's a weight WT. So we have like a weighted WT times f of xt minus f of x star less than equal to 2b square over mu times t plus 1, right? So now we have a result where we have a bound that goes to 1 over t instead of 1 over square root t, okay? And this is because of using strong convexity. So this is a summary of the results so far, right? So we have r square b square over epsilon square. We have in the Lipschitz continuous plus strongly convex case, right? So there's no Lipschitz smoothness. It's just Lipschitz continuity. We have 2b square over epsilon minus 1. So this somehow actually does not depend on r. So no dependence on r. Okay. The smooth case is r square L over epsilon, and the smooth plus strongly convex case is L over mu log 1 over epsilon. Okay. So again, these are examples. I think here you can view this. So this is actually slightly better than this, right? As you can see, it's still bad because the constants can be bad, right? And secondly, it is still not as fast as the smooth plus strongly convex case, but at least it is better than just the continuous case. Okay. Okay. So with this, we'll end here, and next time we'll discuss lower bounds on the gradient descent. So we'll show that the analysis of gradient descent actually is tight, and then we'll look at some practical aspects of gradient descent, like how to implement gradient descent in practice. So we'll talk about line search, and I'll do some demos of some Jupyter notebooks discussing this line search, right? And we'll also talk about then accelerated gradient descent and proximal gradient descent. Okay. Awesome. Are there any questions? Yes, Nathan.
So can you clarify again the conditions that, or rather why we can assume that F would be bounded, or sorry, that F would be Lipschitz continuous and strongly convex, when in general on an open set, I believe we said that that's impossible.
Yes. So your question is, why does it hold on a closed slip?
Yeah, well, I just wanted you to clarify again. Yeah, basically.
Okay. So yeah, so basically, how is it possible to be both Lipschitz continuous and strongly convex, right? So basically recall that Lipschitz continuity requires that f of x minus f of y, right, is less than or equal to L times x minus y, right? So now what I can do is that if my x is bounded, right? So okay, so maybe another way to view this is also by taking the subgradient. Let's assume subgradient, right? HF of x, and the norm of the subgradient is bounded. So actually, I'll call this B, right? Is bounded by B. Okay. So all we need to assume that my x is bounded. So assume that the norm of x is bounded, right? Okay, and the f is well behaved in such a way that if my x is bounded, that means that there exists a B such that the gradient of f is also bounded, right? So think of, maybe we'll take an example, right? So think of this function, which is like, say, the hinge loss, right? I'll call this hinge loss of theta. We know that this function is Lipschitz continuous plus theta square by 2, suppose, right? So now what we have is that if we take the subgradient of this, right? So the subgradient of this is nothing but going to be equal to the subgradient of L H, right, at theta, right, plus theta. Okay. So essentially what this means is the norm of this, so this theta, right? So the norm of this at theta is less than or equal to the norm of L, which is true, right? Because this itself is Lipschitz continuous, plus the norm of theta, right? So the norm of theta is bounded, say, by R, then this is going to be bounded by R, right? So that way we get a bound on this. So essentially that's why for most functions where if the x or the parameter is bounded and the function is somehow well behaved, then we can show that the subgradient is bounded, right? So that gives this kind of Lipschitz continuity. Does that answer your question, Nathan?
Yeah. So again, the improved bound assumes both Lipschitz continuity and strong convexity, but that assumption also comes with the caveat that the parameter is bounded in some way.
Yes, the parameter is bounded and the function is well behaved, that you can kind of if the parameters are bounded, the gradient also is bounded, right? That's an additional assumption, because it could be possible that the function is like wacky, even though it's strongly convex, right? That even if x is bounded, the subgradient is not bounded. Right? But I think that would be rare, because that would mean that the function is not differentiable in the first place. Oh, sorry, I mean, it could be the case that, yeah, so it could be possible the function is growing very strongly and still it is not differentiable and has infinite subvariance, right? So basically, barring all of that, if the function is somehow well behaved, then when the parameters are bounded, it also assume that it will also basically imply that the gradients are bounded. But I think the main assumption for this to hold is that the gradients need to be bounded. That's the main assumption. Yeah. Any other question? Anyone else? So are you going to record? Yeah. So in the recorded lecture, I think I'll go over some of this proof in more detail and also talk more about the bounds a little bit. So hopefully this is clear. But if it's still unclear, let me know. Right? We can discuss this a little bit more next time. Awesome. Thank you. Are there any other questions? If not, then I think we can end. So again, see you next time. I will actually upload the marked up lectures of both 2.1 and 2.2. Yeah. So there was a question. So Harsha, you had a question?
Yeah, I mean, it's a very general question. I saw you use the term step size and learning rate interchangeably, and does those two terms mean same always,
Yeah,
or
the learning rate
is
is
there a
used in
difference?
machine learning community. Step size is used in the optimization community. So both are the same, right? Step size is used in the optimization community because it's related to the optimization algorithm. The learning rate is related to the speed of learning or convergence, right, in machine learning. So it is used in machine learning. Yeah, but both are similar.
Okay, thank you.
No problem. Yeah. So Krishadeja, you had a comment. I see. Yeah, that's true. Do you want to maybe just mention this to everyone? Yeah, Krishadeja? Okay, that's fine. Maybe your mic is not working. So, all right, then I think I'll see you guys. See you guys next week.
Professor?
Yes.
Sorry, I mean, just a quick question regarding the class logistics. So, I mean, I couldn't find I mean, the PDF which you used in the first class, like that explains like, how much the breakdown for each. I forgot. Do you have assignments for this course, or so how does it work?
Yeah. No, so there won't be assignments actually. There will be. So actually, like a lot of this is there on the GitHub page. So I'll actually post it on Teams. I posted it in the beginning of the class. So you have access to the Teams, right?
Yes, Professor.
Yeah. So so basically on Teams, there is the detailed, the detailed breakthrough of the class, the lectures, also the slides, and essentially, the kind of what all is expected in this course. So basically, there'll be a paper reading, and there will be a project. There won't be any assignments.
Oh, okay. Yeah. Thank you.
Yeah.
Thank you, Professor.
Okay.
Yeah. Thank you so much.
No problem. Any other questions? Okay. All right. So I'll see you next week then.